Okay, so the first part is express the volume of the can in terms of H and or. Am I recording? I am. Can we see? Great. Okay, so the first part is volume equals pi or squared H. That's part A. The volume is 330 equals pi or squared H. That's the answer for part A. Does anybody know why this is called the constraint equation? What's the meaning here of that? Does anyone know? If you think about that word constraint. Any ideas?
Constricted.
Yeah, but why? Oh. Like what's happening here? You see, this is called the constraint equation because the or and the h are constrained to obey this equation, meaning that you can't have any or any h. You have to choose an or and a h so that you get a volume of 330. So you're not unlimited in your choice of or and h. Do you understand it? There are some restrictions on it. So this is called the constraint equation. B. Express the cost of the can in terms of h. Now, when we look at the cost of the can, we have two costs to consider because there's two different prices. Isn't there? No, sorry. It's 3p per centimetre squared, 1 square centimetre. Okay. So if you figure out the area and multiply this by 0.03, then you'll work out the cost. So we'll have to work out the area. This is 2 pi r squared, those are the two circles, plus 2 pi r h times 0.03. But I say I only want it in terms of h. Is that right? Oh no, sorry. First part is expressed in terms of h and or. So that's part B done. But then part C is now in terms of or. Isn't that right?
Yeah. Oh.
Yeah. So if you were to take the constraint equation, you could say h equals 330 over pi r squared. So now you get the cost equals 2 pi r squared plus 2 pi r 330 over pi r squared 0.03. So that's equal to, let me see, 0.06 pi r squared, cancel, plus can someone do that for me please? 2 times 330 times 0.03. 19.8 pi.
What about the p? There's no p, is it?
Oh, okay. If you want, you could say it's that many pounds. I'm not writing the currency down. I should, I know. Oh wait, yeah, sorry. It's not pounds, it's pence.
Mm-hmm.
Yeah. So this is pennies. How many pennies? This is, yeah. Okay, maybe I will, just so I don't confuse myself later, just stick at the end P for pennies. So many pennies there are. Okay. Now I want to figure out the minimum. So what do I do here to get the minimum?
dy.
Yeah, the derivative. So that would be 0.12 pi r minus 19.8 pi over r squared. And that's to equal 0, isn't it? So if you rearrange that, you get r cubed. Bring that over to the other side. 19.8 pi over 0.12 pi. The pi's cancel, and then we can cube root. And that's the r. And then as soon as we have the r, we have the h, because we have a formula earlier. Where's it gone? There it is up there. H will be 330 over pi, whoops, r squared. So, what's the r here? Please, when you're ready. And then once we have that, we can get the cost.
It's 5.5.
5.5 pennies. And then if we put 5.5 in here, and then if we put 5.5 in here, tell me what we get for those two, please. And then we have that part done. So what's the height? The height. Oh, it's not pennies. Sorry, centimeters. What's the height? What do we get for h?
3.4.
No, can't be. What? The height is 3.47. That's a small can of Coke.
Even like the R on the book, it's 3.7.
Oh, so it's not 5.5 here. So what's the mistake? Did you cube root? That's it. Can I see? Me no like. Me no like. Did anyone spot any mistake? Let's see.
Oh, teacher.
What?
The antithesis is different. Yeah.
What did I do wrong? Well, I mean, it might be the same, just in a different form, isn't it? Pi r squared plus 2 pi r h. Sigh. Oh, look. Here's my mistake. I can spot it right here. The pi's cancelled here, didn't they? But I wrote the pi here. So, well, no, that's not so bad, because I can just scratch that out. Yeah? Scratch that out. And then scratch that out. Let's see what we get. Cube root 19.8 over 0.12 pi. There we go. 3.75 centimeters. Great. So then the height then, I'm going to assume that the height is right in the answer, 7.49 centimeters. Okay, and then part E is what's the cost. So if you sub in your 3.75, 3.75, that's a 3.75 there. Oh, I've got an eraser. $3.75. I'm sorry, can you see that even? 3.75. If you sub that in, your cost comes out as 8 pennies. I also need to check that it is a minimum. So the derivative here again is 0.12 pi plus whatever 19.8 times 2 is 39.6 over r cubed. Clearly positive, which makes it minimum. Remember second derivative? Yeah.
But the E, if the pi cancels out, why is there still a pi?
Yeah.
Here?
No,
19 point.
E?
Yeah.
Oh! Yeah, I shouldn't have this pi here.
Yeah.
Yeah, thank you. Bloomin' pi.
So the one 0.12 pi plus 39.6, that one is second derivative. The main one.
Does it?
No, is that the second derivative?
This is the second derivative, yeah.
Okay.
Yeah, second derivative. Second derivative. So the last part, the manufacturer discovers he made a mistake in his calculations. The cost of aluminium is twice as much for the top and bottom, since the top and bottom of the can is twice as thick. What is the height and width now? So there is no need to redo all the calculations if you can carefully follow the change. So if the top and bottom cost twice as much, then it means, can you see at this step, this 2 should be 4. So instead of being 0.06, this would now be 0.12. Yeah. So let's track that guy. That's 0.12. And then this guy will be 0.24. And this will be 0.24. So we'll get a different answer if we just change that to 0.24. (3.7 5). Okay, what's the or? If you change that to 0.24 pi and the top is 19.
It's 3.
Yeah, it's smaller. Yeah, 3 centimeters. And the height, what changes in the height? Oh yeah, so instead of 3.75 here, if you could have 3. What you get?
I got 11.7.
Okay, so I think I might have rounded too much in the answer there. I said 12, so 11.7 centimeters then. So when you make the top and bottom more expensive, it means the can's shape has changed. The top and bottom become smaller and the can becomes taller. Which makes sense, right? If the top and bottom are more expensive, then you want to have less of the top and bottom. Right? I think this is more realistic because when I think about a can of Coke, the top and bottom do seem to be twice as thick as the side. Right? Anyways, what is the size of a can? Would it be about 6 centimeters by 12 centimeters? Anybody got one? No? Later. Okay, yeah.
In the book, the answer is 12 and 6.
Yeah, only because my question was, what's the height and width? Although I'm not happy with the 12, I might round it too much. Maybe 11.7 is better. Okay, what's next?
Question 5.
On what page? Oh, that one. Can I scroll down? Okay. Express, guys, are you looking? Guys, number 5. Express the number 8 as a sum of two numbers such that the result of multiplying their product by their difference is maximum. So, let me give you a couple of examples. You want to write 8 as the sum of two numbers, like for example 1 plus 7, so that if you multiply, what did I say? Their product by their difference, was it? Their product by their difference. So what's the product of 1 and 7? 7. And the difference between 1 and 7? 6. So that's 42. What about if I said 8 equals 2 plus 6? Their product is 12 and their difference is 4. And so on. So my question is, what is the sum, what is the pair that will make this a maximum? Okay, so we'll say that 8 equals x plus y. And we want to make their multiplying their product, by the difference. We want this to be maximum. Okay? Well, we'll see now. What's the name of this equation? See, this will be called the constraint. Because, are you free to have any x and y? No. Just like with the last example, you're not free to have any x and y. You have to make sure your x and y add to 8. So this is a constraint. Okay? And this is what we want to make maximum. Let's give it a name. We'll call it z. Now, what's the problem with z? It has two unknowns in it. Well, we can easily fix that. Let's suppose I want to replace the y. What would I replace the y with? Yeah, I could replace it with 8 minus x, couldn't I? Now, isn't this looking a lot better? So this will be 8x minus x squared times 8 minus 2x. Now, what type of equation is it starting to look like? Ah, no. Well, we're well past linear now. What's it looking like? Oh, well, cubic is what it'll end up being, won't it? 8x, so that's 64x minus 16x squared minus 8x squared plus 2x cubed. So z equals 2x cubed minus 24x squared plus 64x. Yep, and now what's next? Derivative. 6x squared minus 48x plus 64 equals 0. Now I'm actually pretty sure that this does not have nice factors. You'll have to use the formula. So x equals 48 plus or minus square root 48 squared minus 4 times 6 is 24 times 64 all over 12. So, what are the two answers here for x? And then 6.3 or... So we'll just say 1.7 for the moment. Okay. 6.3 or 1.7. Now, what's the y value that goes with that? So you can use the fact that x plus y equals 8. So that'll be 1.7 or 6.3. And maybe that's not too surprising, because what's happened here is you said, you could say 6.3 plus 1.7 equals 8. Yeah. Or backwards. So you don't really have two answers here. You really have the same answer twice. So, this apparently is the way you can express 8 as the sum of two numbers so that the multiplication of their product and difference is a maximum. Do we need to check if it's a maximum? Well, let's do a quick check that it's a maximum and not a minimum. So the second derivative is 12x minus 48. If you sub in 1.7, you get definitely negative, which makes it a max. But if you sub in 6.3, you get a minimum. So perhaps it'll be better to say this is... Okay, actually, there is a good reason why you have two opposite answers here for what seems like the same answer. I wonder if anyone knows why. At first I thought both these answers should be maximum because, well, both these answers are basically the same.
Because if you minus from another one, you have minimum, and if you minus like.
It is something to do with the minus, but what precisely?
6.3 minus 1.7 is positive, but 1.5.
That's it, very good, yeah. It's at this step. You realise I said y minus x, but I could have said x minus y. So what's happening is, in the formula, this answer, when you sub it back in, gives you a negative z, and this answer gives you a positive z. So technically, the negative answer will be a minimum then. It's smaller than the other answer, you know. So, how can I put this? It's not that it's wrong here or wrong here. It's just because the choice I made here. So still, it's still only one answer, and it is a maximum because you can actually put the values in and see, as you said, 6.3 minus 1.7 is positive, but 1.7 minus 6.3 is negative. So anyways, I think that matches up with the book. Yeah. Okay. That was a hard one. What's next? More of these. Okay. Yeah. I also am mindful that there's something to do from the lesson before it as well. Number 6. If you have a square sheet of paper, you must cut a square out of each corner in order to fold the sheet up into an open box. How much do you cut so as to make the most volume? So the picture is here, you have a square piece of paper. You cut a piece off of each corner, like this, and then you fold it up. So to make a box. Yeah? And my question is, how much do you cut from each corner to make the volume the biggest? So obviously, if you cut too little, you'll have a very short box, which won't hold much. But likewise, if you cut too much, you'll have a tall, skinny tube of a box that also won't hold so much. So there must be somewhere in between that will give you the most volume when you cut the square out. Do we get the concept here? Yeah, so like if I have a piece of paper, I'm looking for how much to cut so that I can fold it up to make the biggest box. Okay, so let's set this problem up. Now, I don't give you any numbers. You don't really need any numbers for this because you know it's a square. So what you can do is you can just call it a square of side L by L. Okay, and we want to know how much to cut out from each corner, and we'll call that amount x length. The volume, now you'll have to use your imagination. What's the volume here? L cubed? No, because that would be if I didn't cut anything.
L
You can do like
minus
L squared minus
L minus
x
2x.
minus 4x.
Well, hang on, do you know what I'll do actually? It'll be a little easier. If I draw the box in 3 dimensions after I fold it, how big is this side?
L minus 2x.
L minus 2x. And then this side?
Same.
And this?
Same.
No. X. Little X tab. Fold it up. Fold it up. Yeah? Can you visualize that? Yeah. So the volume will be L minus 2x squared times x. So that will be L squared minus 4LX, right? Plus 4x squared times x. Did I get that right? L squared minus 4LX plus 4x squared times x. Okay, so that's 4x cubed minus 4LX squared plus L squared x. That's the volume. right? But we need to differentiate next to get the maximum. So that will be 12x squared minus 8l x plus l squared equals 0.
There's 2.
Oh no.
Oh, no.
Yeah, yeah. Is that okay? Can we factorize? A little bit tricky too. I mean, we could try to factorize it, but no, I don't think it'd be possible. We'll have to use the formula. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. That's 8l plus or minus, is that 16l squared? It is, isn't it? So square root of 16l squared? 4l over 24. So it's either going to be 16l over 12l over 24, which is a half L. Or if you take the minus answer, 8l minus 4l is 4l. 4l over 24 is 1/6 L. Now, we have two answers. We need the maximum answer. So let's get the second derivative here. That's 24x minus 8l. If I sub this into the second derivative, a half L, that'll be 12l minus 8l is 4l, which is positive, which makes it minimum. If I put a sixth L in here, that's 4l minus 8l is minus 4l, which is a negative, which makes it a maximum. So therefore, this one must be the answer. The answer is to cut off 1/6 the length. If you cut a sixth of the piece of paper from each corner, that'll give you the maximum area. Although we know that the other answer doesn't make any sense. Why not? Why is the other answer actually just rejected flat out? Why do this answer is meaningless?
The cube will be too small.
It'd be worse than too small. It'd be non-existent. Yeah. Well, if you cut half the length of paper from each side, do you know? Like, suppose I cut off 1/6, 1/6, 1/6, 1/6, fine. Okay, so if I go in half and cut off half, and then go in from the other side and cut off half, and from the top cut off half, and like there's nothing left to cut. It's all gone. If I cut off half from the left and half from the right, then there's nothing left. Okay, so that one was also a little bit tricky. I've seen this in the exam once. The only difference is the L was a number. It was like a, whatever, 50 centimeter piece of paper or something.
So can you do the 76 and 3?
Yeah. 70, oh, number 3, okay. Now, did we all confirm that the answer for 1B is wrong? Or did it should say falling concave? Okay. Right, let's have a look at number 3 now. Oh goodness, consider that graph. It cuts the x-axis at only the points 3.421 and 0. Find the inflection points and determine the nature of them. Ugh. Why did I make it so hard? I was just making more work for me later. Already out of paper. What's after my x squared? 135 x minus 56. Right, so inflection points need the first derivative not to be 0 and the second derivative to be 0. So first derivative is 15x4, isn't it? Minus 120x cubed plus 330x squared minus 360x plus 135. And the second derivative has 60x cubed minus 360x squared plus 660x minus 360. Now it really, and that's to equal 0. Now it really looks like I can divide by 60. Right? Can't I divide by 60? Is this one, oh, goodness sake. 110? No. 11.
The previous one should be 6.
Yeah, sorry. 6. 11x minus 6 equals 0. Fine. So we're going to have to solve this cubic. Do you remember how to solve this cubic? You did it in algebra. Yeah, but before that. Yeah, but before that.
Graphic.
Before that.
Okay.
You're going to have to find one solution by guessing first, aren't you? Remember?
1 or 2.
I think 1 won't work. Maybe minus 1, maybe. 2 seems more likely as a starting point, perhaps.
2 minus
If you
2.
sub in 2, what do you get? You get 8
minus 12.
plus 22 minus 6. Could that maybe work?
Oh,
No.
Not minus 12. Not minus 12. Minus
Oh, it's not,
24.
sorry. Yeah. Minus 24 plus 22 minus 6. Oh, that works. Because that's minus 2 minus 8, 0. So 2 is a solution. So we found one potential inflection point at 2, but we need to find the other ones. So long division. Right, let's fly through this long division. So what's first here? Come on. X squared. X cubed minus 2x squared. What's that? Minus 4x squared plus 11x minus 6. Minus 4x. Minus 4x squared plus 8x, isn't it? What's wrong?
No, can we just use the calculator to get the answer?
Not in the exam.
Why?
Because I would give the calculator for doing all the hard work. 3x minus 6 plus 3. And that finishes it off. So does this quadratic have solutions? It does. 1 and 3, isn't it? So we have quite nicely x equals 1, 2, or 3. Now, are these all inflection points? Not necessarily, because we have to see what the first derivative is doing at these points as well. So we need to sub 1, 2, 3 into this. If I sub in 1, what do I get? 15? I couldn't possibly get 0, could I? Hussein, could you sub in 1? Matar, could you sub 2 into this one, please? Yeah, and Ishpreet, can you sub 3 into this here?
Can I ask, why do you make the second derivative 0 and not different?
First derivative being 0 gives you turning points. Second derivative being 0 gives you inflection points.
I got 15.
You got,
15.
and what one were you taking?
2.
So,
1, 0.
so hang on, that's okay. You got 15, which is a positive, which means you got here a rising inflection point, and you two got 0.
Yeah.
So that doesn't mean it's not an inflection. Well, actually, it doesn't. Yeah, we have to look at the next derivative to see what happens at 1 and 3. Okay? So, we're keeping track of all our answers. On the side here, I'll just bank one of the answers when x equals 2, we know this is a rise inflection. So I know already that when x is 2, it must be going from what's it, concave to convex. Yes, that looks promising. Okay, so we have that one in the bank. Let's go back now. We have to examine 1 and 3 in more detail. Okay, third derivative. 120x squared minus 720x plus 660. Okay, now we have to try putting 1 and 3 into this fella. So Hussein, could you do the 1?
180.
Huh? I made a mistake. Which one's wrong? I'm differentiating. Oh, sorry, thank you. 60 times 3 is not 120 but 180. Is that what you're telling me? Yeah, thank you. Okay, Hussein, can you put in the 1, and Matar, could you put in the 3?
120.
You got 120 when you put in 1?
Yeah.
Are you sure?
Yeah.
Yeah.
Okay, and when you put in the 3,
120.
you both got 120 for 1 and 3.
Yeah.
Okay, that's good. So if the third derivative is positive, that means we have a rising saddle, and saddle is a type of inflection point. If you look at the picture, you look at the picture. Yeah, can you see in the picture, saddle is a type of inflection point. What? What?
It's not, but
It is.
the saddle is an odd function. The inflection point is concave and convex. Is it the same?
Say that again.
The saddle points are
Are we talking generally or just this question?
yeah, this question.
Okay, fine, go ahead, yeah.
It's an odd function, so it's always in reflection to the origin.
It's not an odd function.
The third. How is
We will learn in semester 2.
it's an odd function?
It's. Are we talking which function? The original function, this one. This one here.
Yeah.
It's not an odd function and not an even function. Which I know is difficult for you to believe because you're looking at the 5.
So if I put minus.
If
1,
you put minus 1 in or 1 in, you don't get the same answer with opposite signs.
Okay.
So what you're thinking of is if you had only x5, you would have an odd function. If you had only x power 5, but not in its current form.
So if I have odd and even function, then I have not even or odd function. If I have odd and even numbers.
Mixed together.
Yeah.
Could be even, could be odd, could be neither. Don't know. But we actually will study this in semester 2. So you'll see how complicated it gets. Right, sorry. So you both got positives, which means both of these are rising inflection points or rising saddle points. Because you can see they go from being concave to convex and concave to convex. So let's go back to our bank. What did we say? X equals 1 is a rise saddle. And x equals 3 is a rise saddle. So if I was to draw this, there's 1, there's 2, there's 3. I'm going to save time and not bother with the y values because you just sub them in and get it. So I think when you put in x as 1, you get a very negative value. When you put in x as 2, you get a negative value as well. And when you put in 3, when you put in 3, Now, I tell you in the question that it has a root at 3.4, so you're slightly below the root here, and the root is like here. This is the root, which I give you in the question. Okay, let's draw it in. So what's happening at the 1? It's a saddle. So a saddle means it's flat, and then it goes up, like the horse saddle. So you sit on the flat horse saddle. It looks like you're at a minimum from one perspective, but a maximum from the other. 2 is an inflection point, but it's a rising inflection point. So it means we're going from convex. Ah, what am I doing? To, oh goodness, this is hard to draw. Let's try this again. Flat. Oh my goodness. And then flat again, and then up we go. So concave, convex, turning point. It's flat, but this is not flat. It's remember, at a positive first derivative, so it's increasing, and it's convex, and here it is concave, and this is flat again, so that's a turning point, and then it increases by being convex at the end. So it goes, I'll shade it in brown here is concave, so concave, convex, concave, convex, and in blue maybe, how can I change colours? Here we go. And this is flat here, and this is flat here, but this is rising. Okay. Yeah, that matches up with the picture. Now the last part here, which I don't have time to do, but I'll just talk about how to do it. I haven't answered the part here that says, show that there are no more turning points. In this graph, how many turning points were there on this graph?
1, 2.
2. But if we go back to the question, how do we find turning points? By making the first derivative equal to 0. Now if you look at this equation, some of you might know this, potentially how many solutions could this have? It could have 4. So we don't know. It could be the case that there are 2 more turning points somewhere else on this graph. How can we check? We would need to solve this equation. But you might say, well, this is very difficult to solve, power 4. However, we have 2 of the solutions already, don't we? What were the 2 turning points we found? 1 and 3. So we know that x minus 1 and x... No, actually, I think, you know what? I will do it. Screw it. Right. X minus 1 and x minus 3. These are 2 of the solutions.
Yeah.
So what you can do is x squared minus 4x plus 3. You can divide that into this.
Yeah.
And what type of equation would you get as a result?
Quadratic.
And how many solutions does the quadratic have?
2.
So we have the option to find all 4 answers now. Right, so let's quickly do this. What's next? Minus 360.
15x.
Oh, do you have it done already? No, I trust you. What you get? 15x squared? Oh, come on, tell me. I believe in you.
I
What?
didn't write down my working.
Yeah, but just give me the answer. I can just take the
I want
answer.
to take the 15x squared minus 60x
Yeah.
plus 45.
Okay. We will all believe you.
45.
Sorry, I mix those 2 up all the time. Right, we'll all believe you that this is right. Okay? I mean, it's not that difficult to do. And if we try to factorize this, I believe we won't find any solutions, because the discriminant here would be 60 squared minus 4ac, which will be 60 times 45, Will that be a negative? No, that's a positive. Oh, maybe you're not right. Alright. Okay, 15x4 minus 60x cubed plus 45x squared minus 60x cubed. What's this now? Plus 285? Is that right? Is it?
Yes.
So what's next? Minus 60x. Minus 60x cubed plus 120x squared minus 180x. 165x squared? Yeah? Minus 180x?
Plus
Plus
6
one.
times 4 is 240.
What? Where?
6 times 4.
Oh, not 120. Thank you. I'm having trouble multiplying by 4 today, or 3, yeah. So, instead I have, what's that now? 45. Yes?
Yeah.
45x squared minus 180x plus 135. Okay, so what's the last fella?
First I said.
Oh, oh, I guess I should believe you. Okay, I've learned something now. So this does have solutions.
That's the same.
Same.
Ah, okay. Why didn't you say so? So it's not that it doesn't have solutions, it just gives us solutions we already have. Oh, okay. So if you solve this, you get x equals 1 or 3. So that's why there's only 2 solutions and not 4, because the other 2 are the same. You kept that from me now. You made me go through all that trouble. Alright, that's okay. I'll remember for next year. Okay. That was a very hard one. Very hard one. Like I said, if you got number 3, then you basically have that exercise completely, fully understood. For exam purposes, really, if you can do the likes of question 1 and 2, you're fine. Sometimes they ask you to make a sketch to show that you understand what a saddle point is, or an inflection point, or whatever. Okay? Yeah.
I don't get that. What is the difference between inflection point and saddle point?
The only difference between an inflection point and a saddle point, and really a saddle point is a type of inflection point, is saddle points are flat.
Okay.
So I suppose you can put it like this.
I mean, can I use them exchange?
No. But what you could say is all saddle, guys, this might be something worth noting. All saddle points are also inflection points. But not all inflection points are saddle points. So the difference, just to be clear, guys, come on, just to be clear, inflection point just means you switch from being concave to being convex. Whereas a saddle point means really the same thing, except that the point also is a turning point, it levels off. So this is also an inflection point because it goes from being concave to convex. This is an inflection point because it goes from being concave to convex. But this is a special inflection point. And this special inflection point, we call it a saddle point because it's it levels out in the middle here. Okay? So like I said, all saddle points are also inflection points, but not all inflection points, like this guy, is also a saddle point. Does that clear it up for you? Yeah. Okay. Saddle points are interesting because they sometimes make us think we have a maximum or a minimum, but then we realise we don't. with a saddle point. And inflection points are interesting because it represents a point in the graph where the behavior has changed. So, like in biology or something, like I said, you know, maybe you have some process that reaches a point and then changes into something else, you know. All right, we'll finish for sure.
Yeah.